Okay, to take a look at the lab that you just did, you were supposed to draw the electrons and protons as they would move or kind of where they would be throughout the entire process. So for that, there are a couple of things we wanted to see. You should have gotten from your data that after rubbing, that pink foam had a negative net charge. So that means that I drew the positives and negatives there as a neutral before rubbing to kind of let you catch up with me and not have to draw all of the positives and negatives to start, but just the kind of the ones that are important. So if it's a negative net charge, this thing has extra electrons. And those extra electrons are kind of sitting right on top there. For the next part, you bring the pie pan near and take it away and test it, and you should see that it was neutral still. The pink foam is still negatively charged, so we still will leave our extra electrons, I put 4, on that pink foam. But let's go back to the pie pan. It's not positive, I have no electrons there, so I definitely need to add electrons to match each of these pluses, or each of those protons. But we do know from before that those electrons in a conductor, this aluminum pie pan, are going to see this negative foam and want to be as far away from it as possible. So they're going to go to the opposite edge. It's still neutral, but we would just consider this polarized. This would be my partial negative side and my partial positive side. You would have an attraction between the two, but we didn't really notice it because those are such big items that you're controlling them by holding them, so you wouldn't have felt too much of an attraction just from holding it. All right, moving on, it says, what's happening while touching your finger to the pan? And if you didn't notice, you got a shock. And that shock meant something was happening, but in order to kind of assume or hypothesize what happened, you need to look down at the next picture. And that is where it was again asking you to test the charges. So after you touched it, you test the charges, and the pie pan had a charge. And that charge was positive. The pink foam was still negative. So if the pie pan becomes positive, that means that those electrons, the 4 that were kind of balancing out the 4 protons, had to have left. And so maybe I'll leave one here, but show with arrows that that electron has gone into your hand along with the other 2. I didn't have you test your hand, but you're so big you wouldn't really have been able to see a reaction to the tapes, likely. Okay, so that's what's happening on the pie pan. Because it was polarized, those electrons were like, I want to be as far away as possible from this, oops, we got to show our negatively charged foam, and they wanted to get far, far, far. They went to the top of the pie pan, but as soon as you put your hand there, they were excited to see you because they could get even further away from that pink foam. So they went into your hand. So that leaves the next one, a net charge that's positive. We can leave 1 electron on there. You could have left 2. It doesn't really matter. Maybe a lot of electrons went, but since we're only drawing 4, it's kind of unrealistic to say that you're going to leave something with no electrons. So this still has a positive net charge by the 4 protons and 1 electron. And then the foam was still negative. After you bring them far away, that electron will settle back, and this was still positive, and this was still negative. So that electron might kind of go back to the center. It's not trying to be repelled by anything macroscopically, but this one still has its charge on top. So that's what the diagramming looks like, which we will continue on with in our next lab, so kind of keep that in mind for a good way as to how to figure out what's happening. The back side of this is when we're going to talk about what is this really called? Because there is a specific name for it. And to talk about that, we have a few vocab words to go over. So, in general, the thing that you did when you touched the pie pan, you grounded it. And I'll even write that in. You grounded the pie pan, and that is our new term. A ground is defined as a large source of electrons. And then, yes, it does have protons. But so many that it doesn't matter if you take an extra few. So when you touch the pie pan, you as the person are so large and you have so many protons and electrons already that a few extra electrons is like change. It doesn't really affect your net charge, although you might have an extra electron or two. In the scale of how many you own, it does not change your net charge, as we say. It's kind of like a trillionaire having an extra penny. So the ground can be you, as long as the object that you're grounding is smaller, or the ground can quite literally be the earth. Oftentimes, anything in our room, anything that's connected to the earth, particularly some lab tables, things like that, you'll see as the ground. So again, a ground is a large source of electrons, and it does have protons too, but it is so massive that it can take or give an extra electron or two. And I guess quite literally, it could take or give multiple electrons. It doesn't have to be just two. The procedure is quite simply what you did. Touch the charged object, or touch the object to a ground. It could be a charged object, it could be a neutral object, it could be a polarized object. It is going to cause a transfer of electrons if it is charged or polarized. If the object's neutral, you're likely not to take any or give any electrons to it. All right, for induction, this entire process of what you did, polarizing something, touching it or grounding it, and then separating the two, leaving it with a net charge, leaving that pie pan with a net charge, is called induction. So in general, it's when an originally neutral object is polarized and then becomes charged. In our example, we did this by grounding while polarized. It does work best for conductors because conductors are the easier ones to polarize. And the procedure to do this is simply polarize something and then to ground it. So that's just a little bit of a summary of what that means. We're going to keep comparing these things that we've learned to each other. So I have a little chart here that's going to ask you some questions. You can try to fill it out on your own and pause and then come back and hit play when you want to see what they are. Okay, for polarization, remember we brought things near the charged object, so no. Charges did not transfer between the two objects, they just moved in the neutral object, so no. Polarized objects did not gain a net charge, and so therefore that is not applicable. For induction, the contact was not made between the charged object and a neutral object. The contact is meaning the contact between the pink foam and the pie pan was not made. Charges transferred between the charged object and the neutral object? No. And causes change in net charge? Yes. Our pie pan did change its net charge, and it was changed due to grounding. So electrons either can go into or out of the ground. This object became oppositely charged as the originally charged object. So our pink foam was negative, the pie pan became positive. And for grounding, it's kind of not talking about the charged object and the neutral object, but more or less talking between two things. So grounding, we can say, yes, there is touching, but you're just saying touch the object to the ground or you. And so yes, contact was made, but it's really more of a description about you and the object. Do charges transfer? Yes, but again, it's between you and the ground. Does the net charge of the ground change? And the answer is no. Really, it's so small that we say no, because it's like pennies for a trillionaire. Okay, that's it.